Colours. They tell us about the changing seasons, whether someone is interested in us or not, and even if we're feeling angry. In dermoscopy, colours are just as informative. They'll help us understand how the skin is changing, whether we should be concerned, and if those changes are good or bad. In this video, we'll be decoding those colours. I've also prepared a summary sheet for you to download, so no need to take any notes. The skin has its own palette of colours to work with, unless of course you add artificial colouring. When mixing or overlapping, these colours create the range of hues we see. First, let's understand how these colours are produced. Only once we know that can we interpret what they mean. The skin has two primary chromophores. First up, melanin. Melanin is black, right? Actually, the skin produces two types of melanin, which is important. Eumelanin, a black-brown, the most common form, and pheomelanin, a yellowy red, less common. The cells responsible for producing this melanin are called melanocytes. Yes, I know medicine can be simple sometimes. However, each melanocyte can only produce one of these two types of melanin. The ratio of these melanocyte populations in your skin is genetically determined, and that's why there is such a wide range of skin tones. Melanin's main job is to absorb light, especially the harmful ultraviolet light that damages cells. It's 99.9% effective at doing this, and that's why we perceive melanin as being dark. The more melanin you have, the darker it appears in the skin. But where is melanin located? It's not in the melanocytes themselves. They are the factories. They ship their product to keratinocytes, the main cells in the epidermis, to protect their DNA in the nuclei. So when examining normal skin with a dermoscope, you'll actually find melanin in the keratinocytes. However, when something goes wrong, melanin can end up in the wrong place, and that's where things get really interesting. You can thank this guy for explaining why the colour of melanin changes depending on its depth within the skin. Let's look at some examples. In moles, which are abnormal melanocytes, now called nevi cells, retain melanin. They become enlarged and the cells multiply. When these nests of nevi cells are at the level of the dermoepidermal junction, melanin appears in various shades of brown. In an atypical nevus, these aggregated globules are various shades of brown due to different concentrations of melanin and their varying depths within the skin. When melanin is more superficial, as in this superficial melanoma, it appears very dark brown or black. The Tyndall effect has minimal effect here. When melanin drops deeper into the papillary dermis, it takes on a greyish colour. This subtle shift in colour was one of the hardest skills for me to learn to recognise, but with time and practice, you'll spot this grey colour. In the reticular dermis, melanin appears blue, as seen in this blue nevus. Now, pigmented basal cell cancers have melanin because the BCCs release chemical signals like stem cell factor that attracts nearby melanocytes into the lesion. Once inside, these melanocytes produce melanin that gets deposited into the BCC and its colour depending on the depth within the skin. Here are the key takeaways. Melanin's colour depends on its depth within the skin. The colour doesn't tell you which cell type the melanin is located in, however. Our second skin chromophore is blood. Hemoglobin in red blood cells absorbs some wavelengths of light and reflects others, giving us the red colour. The exact shade of red can vary from bright red in oxygenated blood, to blue when it's deoxygenated, through to a purple, and then to black if it becomes clotted. Quick summary of blood. Hemoglobin absorbs light reflecting a red colour, and its degree of intensity depends on its oxygenation and whether it's clotted or not. You might be wondering, how can I tell if black is clotted blood or superficial melanin?
That detective is the right question.
Take this toenail from a 25-year-old patient who came to see me. Is this a melanoma? The answer? We rely on other clues. In this case, the periphery shows red-brown globules that are disconnected from the main pigment, along with a gap from the nail matrix. This is just blood under the toenail. This is a common question you'll face in primary care dermoscopy. Is it blood or is it superficial melanin? Brown can be tricky too. In seborrheic keratoses, the abnormal keratinocytes often contain no melanin, all the way through to a lot more melanin than normal. And deciding whether a brown globule is a dark comedo-like opening in a seborrheic keratosis or the melanin within a melanoma can be difficult. This matters because one is benign and no harm, and the other can be life-threatening. Keratin makes up 90% of the dry weight of the epidermis and is the main structural protein packed into keratinocytes. So what colour is keratin? Take a guess. It's actually colourless or translucent, so it's not technically a true skin chromophore. It often looks white due to light reflection and may have a slight yellow tinge due to contamination with skin oils, lipids, and a tiny bit of melanin thrown in for good measure. This image shows a squamous cell cancer, which is a cancer of keratinocytes. The white appearance is a mass of keratin with a slight yellow tinge. The white reflection here is from the keratin scales. Other examples of keratin include milia, which are small balls of keratin cysts that appear white due to light reflection. And this squamous cell cancer on the arm showing white keratin scales. The larger keratin mass has a yellowish tinge with some orange-yellow deeper colours within. And this keratoacanthoma has a mount-like summit of yellow keratin. Summary: keratin within the skin often looks white due to light reflection and may have a slight yellow tinge due to contamination with skin oils, lipids and melanin. Another example of disordered keratin causing a white structure is around skin adnexal openings. These are often at white circles or under polarized light can show up as an artifact producing rosettes, these 4 dots of light. In the dermis, we have collagen as the key structural protein, making up 80% of its dry weight. Like keratin, collagen is colourless and therefore not also a chromophore. However, as collagen ages, it loses its structure, a bit like me, and it then reflects light. Altered or newly formed collagen can give off shiny white structures, which can be seen on dermoscopy, dermatofibromas for instance, or some melanomas. Sebum is often seen in swollen sebaceous gland hyperplasia, and this appears as a yellow-white, a bit like popcorn. White can also indicate a complete lack of melanin, as seen in vitiligo or halonevi, where the immune system attacks the melanocytes, destroying melanin production in the skin. Flat white regression structures are also seen in melanomas for the same reason. And here's my summary diagram, which I hope you find helpful. You can download it from the video description below. And remember, dermoscopy is the art of decoding histology without resorting to a knife. Now, continue your learning by perhaps watching this video here. Training a primary care dermoscopist for every general practice.